Okay, great. Then let's start. So today we're getting back on the two geometric realization series, and we're happy to have Tsao-Hsien Chen from University of Minnesota, and he's going to tell us about two geometric realizations of the anti-spherical module.
Okay, thank you. So today I will explain this the work of sorry, Akimoto and Canonical, where he give a categorization of anti-spherical module. So the goal is as follows. So we have this anti-spherical module for the affine Hecke algebra. So where H is the affine Hecke algebra, and the F is the finite Hecke algebra, and we can form this tensor. And this is the right model over the affine Hecke algebra, and you admit two realizations. One is in terms of this Iwahori Whittaker function on the affine flag, and another is in terms of equivalent case theory on the dual Springer resolutions. So this is due to Cauchy-Lustig, and this isomorphism plays a important role later when we talk about two realization of the affine Hecke algebra. And today I will explain a codification of this isomorphism. So namely, we'll replace the left-hand side by the so-called Iwahori Whittaker category, and the right-hand side is the equivalent Dirac category for the Springer resolution for the dual group. And what this is due to Akimoto Canonical. So that's the goal today. And so my talk will consist of two parts. So first part, I will explain the constructions from the equivalent Dirac category of Springer resolutions to the affine Hecke category. And this functor denoted by phi diagonal. And the reason is that later we will see that actually this functor is isomorphic composition of this delta star induced by the closed diagonal embedding of a Springer resolution to the stammer, and then composed with the two realization equivalence. Okay. But today we don't we will just so today we'll just construct this map, this functor. That will be the goal for the first part. And the second part, I will explain that the composition of this V diagonal with the Whittaker averaging functors. So we get a functor from the equivalent Dirac category for the Springer resolution to the Iwahori Whittaker category. And this is the equivalence. So this is the desired equivalence. Okay, so that's the plane. So some notations. So we fix algebraic closed field and local field, ring of integer, and we'll have a dual group G. We fix a dual, fix a Ridati group G over K, and the Borel, and also the dual group, which is denoted by G check, and same for B and the Maxima torus and the unipotent radical, and so lambda is the co-weight of T, and we have the dominant co-weight, which is denoted by lambda plus, and we have the finite Weyl groups, extended affine Weyl groups, and most importantly, this curly B is the flat manifold for the dual groups, and also N tilde and N will be the Springer resolutions of the nilpotent cone for the dual groups. So I don't want to write uncheck delta. So, and also the reason will be clear later. And the flag FL will be the affine flat manifold for the group G. Okay, so these sound standard notations. And now, so recall our goal is to construct functor from the equivalent Dirac category to the affine Hecke category. So I will start with some general discussion about constructing a functor from the equivalent Dirac category to an arbitrary additive monoidal category. So how to construct such a functor? Well, first we will use the following restriction of a equivalent Dirac category of a Springer which basically goes back to Sayre. So Sayre gives the description of a coherent shift on projective variety in terms of a gradient module over its homogeneous coordinate ring. So we'll, as a quotient of the gradient module of the homogeneous coordinate ring. So we'll basically apply this idea to our situation, the Springer resolution. So the idea is as follows. So the Springer resolution is by definition, a limit close embedding of this product, the flat manifold times the dual Lie algebra. And we have this T-torsor here. So G check my U check is the basic affine space. So we have a natural projection here. And we have this affine open embedding where this G check my U check bar is the affine closure of the basic affine space. So here, so the error here is similar to the error here. So there's this projected n space. We have these GN torsor and the affine completions. And now this the map here induce a similar map on Springer resolutions. So from here, base change, we get the T-torsor over the Springer resolution. I denote my n tilde head. And then later, I will explain there are certain kind of affine completion of these T-torsors inside this closure of basic affine space times the dual Lie algebra. And then by general fact, the Dirac category here will be a quotient of certain equivalent Dirac category of this affine closure of this T-torsor. And then we'll construct, with this in mind, we'll construct the functor as follows. So first, we'll assume that we have monoidal functors from representation G check to T check to C. This is a reasonable assumption because if we can construct such functors, then because this quotient n tilde mod G check is the same as this one, then you will get a functor from rep G check to T check to C. So if we can construct these functors. So therefore, we just first start with this. So this is given. And then we'll try to upgrade this functor to the category of, so first to the category of free coherent shift on this quotient stack of this affine closure. And we'll do this step by step, 3 steps. So first, we try to, so this is given, and try to upgrade this to this quotient of the dual Lie algebra, and then upgrade this functor to this quotient, so the closure of basic affine space times G check. And then we will show that this functor, under a certain assumption, this functor factors through this closed subscheme, this affine closure. Okay, and then this functor, the last step here, induce a functor between the homotopy category. And then we will argue that, again, under some assumptions, this functor will descend to a functor on the quotient. So here is the Dirac category of a Springer, which is a quotient of this homotopy category. And here is the quotient of the homotopy category of C by acyclic complexes. So here's a general discussion. You don't see affine flag here. And later we'll apply this general construction to our situation and get a functor from, from the Dirac category to the affine Heck category. Okay, so now we'll first do step 1. So step 1. So again, we assume we have a functor from rep G check times T check to some monoidal category C. And our goal is to upgrade this functor to a functor from the quotient staff G check to C, where T check acts trivially on G check, and G check acts on the Lie algebra by the adjoint actions. And turns out to construct such a lifting is basically equivalent to have a tensor endomorphism of the restriction of our functor to rep G check. So tensor endomorphism means that it satisfies this identity. And any such tensor endomorphism will give rise to a unique tensor lifting of our functor F. So there will be a lifting of our functor f. And moreover, this functor satisfies the following fact. It will send so-called a certain tautological endomorphism of the source category to our to the tensor endomorphism. So that's the claim. And so let me first explain what is this tautological endomorphism. So recall that for any equivariant shift on this shift on this quotient stack and any element in the Lie algebra, the equivalent structure on F will define the action of first on the centralizer of X in the dual group G check, and then you can differentiate this action. So you get the action of the centralizer of X in G check on the fiber. Okay, so it comes from the equivalent structure. And then this tautological endomorphism is the unique endomorphism of F such that at each fiber, the endomorphism is given by the action of X on the fiber. And notice that X is in the centralizer. So we have this canonical endomorphism. And the claim is that this functor will send this endomorphism, this canonical one. We apply this to this particular object. It's a free object. And then this was sent to the tensor endomorphism. So that's the claim. And let me give a sketch of proof. So basically, you can assume our target category is of this form. So it's a free module over certain commutative algebra with G-check and T-check actions. And our functor is very simple. It's just given by, it sends a representation V to E tensor V. And this tensor product has is a free object and has a canonical action with G check times T check. So we have these reductions. And so this reduction is explained in the paper. And so roughly the reason is that by some general construction, you can assume the target category is a tensor category. And then this algebra E is basically the de-equivalentized, the home in the de-equivalentized category, which is by definition this guy. And you can check that this is a commutative and has a natural action with G check times T check. Okay. And now, and then in these situations, then this tensor endomorphism, then this N becomes a tensor endomorphism of this very simple functor. So V goes to E tensor V. And now, so according to, so Maki explained this. So such a tensor endomorphism is the same as basically a family of element in the Lie algebra. And it's a G check times T check equivalent map from the spec A to E. So family of equivalent endomorphism of your tensor functors. And this is the same method, just you have a G check times T check equivalent map on ring of functions. So ring of functions on G check to this algebra E. And then you are basically done, because then the functor, the lifting, is given by, it's defined as follows. So on object, it's very simple. Just send this free object to this free object. But the whole point is that you can define the map on home space. And the home space induced exactly by this map. So you have the home space can be identified with element here, and same on the target category. And our map is Bn is G check times T check equivalent. So therefore, it induces a map on home space. And then you are done. So then you get a functor. And you can easily check that this map will send this tautological endomorphism to the tensor endomorphism. So that's the first step, the construction of lifting to quotient of Lie algebra G check. And now step 2, we will try to upgrade the previous functor to this quotient. So now we throw in this closure of this affine scheme, this closure of the basic affine completion of the basic affine space. So how to upgrade our functor to here. Well, so here first I have to remind you some recall some structure, some result about the ring of functions of this affine closure. So first we have the identification of a ring of function of this affine closure of basic affine space as G check times T check modules. So V lambda is the illusory representation of I squared lambda, and minus lambda is the inverse of the representation. So recall that lambda can be identified with a character of T check. So, and this is the inverse. And the isomorphism here is basically the follows from the Peter-Weyl theorem. And then we have then we have the multiplications map. We'll send this copy direct summing and this times this direct summing to here. And this is induced by some canonical, the canonical map from V lambda tensor V mu to V lambda plus mu. And these multiplications will give rise to a map B lambda here, where it's just is induced by multiplication. So it gives a map from V lambda tensor minus lambda times the ring of function to here. Then you just multiply lambda on both sides, you get this map. So this is induced by the multiplication map. We think of V lambda as an element in the ring of functions. So this is a map in this category, and this map by construction satisfies this diagram. So this community diagram, usually called the Plugger relations. So here you start with V lambda tensor V mu, tensor with a ring of functions on the affine closure. You can first do multiplications on the first two copy and take this B lambda plus mu, or you can first take B lambda tensor B mu, and then here you have a canonical identification of a tensor product of a ring of functions. So we have these Plugger relations. And now with this in mind, then the second, the step 2 follows from the following claim. So recall our starting point input is a tensor functor from G check, rep G check times T check to C. And now suppose we are given an arrow f v lambda to f lambda. So this lambda we think of as a representation of T check, and v lambda is a illusory representation of highest weight lambda. So suppose we are given for each lambda an arrow like this, and it satisfies the similar Plugger relations. And then the claim is that then there is a tensor lifting of our functor f to the quotient stack for the affine closure, the quotient stack of the affine closure of basic affine space to C. So to construct such a lifting, all you need is this arrow, and this arrow satisfies these Plugger relations. And moreover, this functor on the level object, it just send this free object to FV. And we'll map the B lambda, we construct the map B lambda here to this well, little B lambda. So that's the claim. And well, the proof is very similar to the previous one. Again, you can assume the target, this category just module over this certain commutative algebra E equipped with action of G check times T check. And then our functor is given by on V is send V to V tensor E and F lambda to E lambda. So where E lambda is as a vector space is the same as E, and and also as a G check representation are the same, but you twist the T check actions by lambda. And you change the equivalent structure of T check. And this B lambda, this arrow is just a map from V lambda tensor E to this E lambda. So we can reduce to this case. And then this assumption, the claim in assumption will allows you to define a map here from the real function of a affine closure to E. And then you're done because we, on the level object we know you send the free object to the free object. But the most important thing is that you how to define a map on home space. But every time you have this map, you can define a map between home space. Okay, and the map is given by this formula on the summation is given by this map, where it's a twist of this arrow by minus lambda, and then you can check that this is a G times teacher equivalent ring homomorphism. So you have this map, and then you're done, basically. Okay, so therefore, a tensor endomorphism plus these plural relations for this arrow will give rise to a monoidal of lifting of our functor to this quotient stack, this closure of a basic affine space times G check. So that's step 2. So now step 3. We want to show that the functor reconstruct factors through this closed affine, this closed substring, this affine cone. And but for this, I have to first explain you the definition of this affine completion of this T-torsor over Springer resolutions. And then I will explain that our previous functor actually is defined on the quotient of this big space actually factors through this closed affine subscheme. And so this guy is basically so first there's a tautological vector field on the product. So whose value at the point yx is given by the vector field, the value at this point is given by ax0. Here, this ax is the action vector field. So namely, on the product, there's a canonical because the second factor acts infinitesimally on the first factors. So yeah, this is a canonical action vector field. And this affine subscheme is basically the zero locus of this canonical vector field. But more precisely, because this is a singular thing, so more precisely, this vector field will define the derivation on the ring of functions. And then the idea of this guy is generated by the image of the derivations. That's the precise definitions. And by construction, you can easily see that. So we have this affine closed subscheme of this product. And if you base change to this G my U times G, you get this T-torsor over Springer. So that's it's a kind of easy to see that this affine closed subscheme satisfies this property. And so our goal now is to show that our previous functor under certain assumption factors to this affine closed subscheme. So here's the claim. So we have in the previous 2 steps, we construct this functor of the quotient stack on this product. And now the assumption is that assume we have this tensor endomorphism from the step 1 and this arrow in step 2. At this level, they don't talk to each other. There's no relation. But now you assume that they satisfy these equations. The composition is 0. So n lambda maps fv lambda to fv lambda, and b lambda is this arrow. So if this is 0 for all lambda in a dominant co-weight, then this functor the functor we construct in the step 1 and step 2 actually factor through the closed subscheme, this untilted head affine. And the reason is the proof is simple. So basically, again, you can replace C by this category of module over certain algebra E. And our functor F tilde is induced by the map from the ring of function on the product to E. And all you need to do is to show that this map factors through the ring of function of this closed affine subscheme. And this is basically follows from this diagram, namely, so this map is the image of the derivations under this map. And turns out this map is the same as basically the composition for NV lambda and B lambda. It's a straightforward checking. So therefore, since we assume this is zero, this map will factor through the quotient, which is the ring of function on the affine closed subscheme. And then you're done. So therefore, actually, our functor factors through this the free coherent shifts on this quotient stack. Okay, so now is the final step. So now I want to show that the functor we can construct how to construct extend the previous functor to the functor from the direct category of a Springer resolution to this quotient of this homotopic category. This is the homotopic category C module cyclic complexes. Okay. So here's the idea. So first, from the previous, in step 3, we construct this lifting. So now it's the quotients of this affine cone inside the product. And now it gives rise to the functor between the homotopic category of complexes. So far, you don't need any assumptions. And now let's consider this full subcategory of this homotopic category consists of a complex whose cohomology are supported on the boundary. So we can consider this subcategory, consider complexes whose cohomology are supported on the boundary of this affine cone with respect to this T torsor. Okay. Now here's the claim. So now we assume some assumption on the target category. So I assume there's a monoidal functor from our C denoted by GER, and the reason will be clear later, to representation of a T check, such that the following two kind of artificial properties. So first, this tensor monoidal functor is compatible with our tensor functor, the input tensor functor, in the sense that the composition is factors to the restriction and then the natural tensor product on rep T. And the second property is kind of this functor is conservative in the sense that if we make a complex to a cyclic complex, then the original complex is cyclic. So if there's a functor like this on the target category, then the claims that then our functor will map those complexes with cohomology, whose support whose shift cohomology are supported on the boundary to a cyclic complexes. So that's the claim. So and the reason is that, well, here's a sketch of proof. It consists of two steps. So basically, you first prove that it will map so the Causal complex associated to this arrow to a cyclic complex. So namely, our this functor between the homotopic category will map a cyclic, this Causal complex to a cyclic complex. And this is because to check this, you can pass to associated gradient. And then the associated gradient will be a complex in representation of T check. And that's just nothing but the Causal complex for this canonical map. And it's known that this map is cyclic. So therefore, by the property that the original complex is a cyclic. Now, the second fact is that any complex whose cohomology is supported on the boundary is a summing of a tensor of this tensor, F tensor, the Causal complex for some lambda. So if assuming those two things, then we are done, because this will implies that our functor will map complexes whose cohomology is supported on the boundary to a cyclic complex. And the second fact basically follows from the fact that if I have a complex whose cohomology is supported on the boundary, then actually this B lambda will be 0 on the support of F for some lambda. So therefore, our Causal complex becomes a kind of trivial complex. Differential is 0, and the tensor product will be just the direct summing like this, direct sum like this. Then you're done. Okay, so this is a scheduled proof of this claim. So assume we can construct this functor on the target category. And now here's the last step. So then our functor between homotopic category will factor through these quotients, because it will send these things whose cohomology supported on the boundary to a cyclic complex. So therefore, it induces a map functor between the quotients. And now its general fact that this quotient is actually equivalent to the direct category of perfect complexes on the quotient stack of this T-torsor, and which can be canonically identified with direct category perfect complex on the quotient of the Springer resolutions, because this head is the T-torsor over n tilde. But then the Springer resolution is smooth. So therefore, the perfect category is the same as the bounded direct category, equivalent direct category. So therefore, so we get a functor from the direct category, equivalent direct category of a Springer resolution to this category. And that's the general construction of so how to construct a functor from, one way to construct functor from the direct category to certain monoidal monoidal category, say. And so let me just the following remarks. So later we'll talk about, we'll apply a similar construction later to the case of a Stamber variety. And turns out you can, from this discussion about, you can construct a perfect direct category of Stamber to the target category. But because the Stamber variety is not smooth, so actually to extend this from here to here in the two realization situation in the Stamber variety case requires actually a lot of work. So you have to do some kind of functional analysis in homological algebra to extend this functor to the direct category coherent sheet. So for example, I think in Roman's paper, he spent like the whole section 7 or 8 is about this issue from here to here. But in our case, Springer resolution is nice, it's smooth. So after we construct a functor from the perfect direct category, we are done. Okay, and so this is a general construction of a functor from the equivalent direct category to monoidal category. And in the next part of the talk, I will explain, we'll apply this construction to our situations. So where this C will be certain monoidal category inside perverse shift on affine flag. So, okay.
Okay, great.
End of part 1.
Yes, let's take a 5-minute break. So we'll meet back at 3:40.
Can I ask a question about this causal complex? Can you go back to that?
Yes. Here.
Yeah. So that causal complex is not like some naive causal complex, like a tensor product of two-term complexes.
Well, it's you have this, then you can always form the corresponding causal complex.
Well, I'm just trying to figure out what you mean by causal complex.
Well, this is so every time you have maybe you have to, so every time you have a section of a vector bundles, then you can form the causal complex.
When you have a collection of sections of a vector bundle?
Oh, just one section.
Just
Of
one
a
section.
vector.
So what's the causal complex then?
Oh, there's a how to write? We can, let me write this. I think you have just, so you have this maybe all to the sections, and then you can maybe we check, then you take O to O, then you can form, I think you can form the causal complex like that. Something.
I see. So in the case when V is a line bundle, this
Then
is
yeah, if you have some twisting, you first, so our situation is like V to some line bundle, but you can first tensor with inverse.
no, that's not what I was saying. I was saying when V is a line bundle, then this causal complex is just this two-term cone.
Yeah,
of
yes.
Yeah, all right. Of the cosection.
Yes.
And okay, but this is just, so this is just the causal complex of one, and in the Grothendieck group.
Sorry.
The causal complex in this Grothendieck group, the fact that it's 0, is giving you some statement. And is it basically the statement that V is the sum of its weight spaces? Or is it something, what is the statement that you get?
Yeah, I think it's a sum of the weight spaces. But the point here is that somehow this causal complex is somehow a cyclic on this G check mod U check. It's not a cyclic on the boundary, on the affine closure. Actually, you can look at the co-kernel of this B lambda.
Right.
Yeah, the point is that somehow the co-kernel detect the boundary.
Yes.
Somehow. Yeah, that's the whole point. So therefore, if you have something which is cohomology, the cohomology is supported on the boundary, then you tensor with this causal complex, then this differential will be 0. So therefore, you actually, this is some trick that using. So that somehow you use this to detect the.
Right. Okay. So actually, I just want, okay. So there is an exclusion principle. So it's very interesting to me that this one map corresponding to the highest weight space should give you this causal complex that categorifies some statement that V lambda is the sum of all of its weight spaces. Like, how does it understand all the other weight spaces? It's kind of interesting, right? Is that? But it seems like an inclusion-exclusion principle does. Maybe I'm wrong.
What is inclusion?
No. I don't know. Never mind. So what does it say on the? What does this say on the? It says that this alternating sum of shifted exterior products is equal to top weight space.
Yes.
But what does that come down to?
So basically, you want to restrict this causal complex to something like representation T check. Just look at the weight space.
Yeah, right. Yeah, if you restrict to representations of T check is what I'm asking, basically.
Yes. And what is your question? So then you can form the complex.
It's very interesting. can I ask another question? So
Sure.
I understand how this mojo of understanding the structure sheaf of G mod U basically gives you this natural transformation from FV to F, from F of the highest weight. Does it naturally give you more of this filtration? Does it give you a map from the kernel of that to, you know, sub highest weights, or is that all part of the same? Does that follow from the same structure, or is that additional structure?
Sorry,
I'm asking whether you get a
the kernel of what? Kernel.
directly.
Sorry, the kernel of what you say?
The kernel of the natural map B lambda.
Mm-hmm.
Does that naturally admit any natural transformations to things in the torus, or is this only going to come later when you change what spaces you're working over and you have Akimoto filtration?
Oh. I have to think about this. So maybe. I don't know. I have to think about this.
Thank you.
So Mackie just said he had some issues with volume at the moment. So maybe we can continue.
Oh, okay. So we continue the second part.
Yeah.
Huh?
Yeah.
Okay, great. So so now the second part will apply the general constructions in the first part to the following situations. So we'll consider the direct category of the affine Hicks category, and we have this abelian category of perverse shifts, equivalent perverse and affine flag. And so for any element in the extended affine world, we have the corresponding orbits and the costandard, standard, and the irreducible object. So our goal is to define this category C in the first part. And for this, there are two important inputs. So namely the so-called Akimoto shift and the category central shift. So let's first talk about Akimoto shift. So here's the definitions. So let's consider J lambda, which is equal to this J lambda star if lambda is dominant, and J lambda 3 if minus lambda is dominant. And in general, it's given by these convolutions. For any lambda, you write this as a lambda 2 minus lambda 1, where lambda 1 and lambda 2 are in the dominant. And we have the following important result due to Mokovich. So this object is actually in the abelian category of perverse shifts. And secondly, we have this property that J lambda convolved with J mu is equal to J lambda plus mu, where lambda mu are any co-weight. And now, because those two properties, we can define this C to be the full subcategory of inside these perverse shifts, which admit so-called Akimoto filtrations. So we consider this category. So namely, consider those objects has a filtration with subquotient are this Akimoto shift, J lambda. Lambda is in our co-weight. And the theorem above implies that this is has a natural monoidal structure. So we can define we'll consider some smaller category inside the category perverse shift. And this C will be the C in our previous, in the first part. So that's the first important input, the Akimoto shift. And now the second important input is the category central shift. So recall we have this central shift functor from rep G check to the perverse shift affine flag. This is given by the nearby cycle functors. So we denote the image by ZV. And now, so I will list several properties of this central functor. So first, it's a convolution exact, means that it convolve with a perverse. If you convolve the central shift with perverse, it's again perverse. And the second property says that it's it's a central. So it's ZV convolve with F is isomorphic to F convolve with ZV. And basically the first two properties will imply actually very interesting result that the central shift is actually in our this category C. So admit the Akimoto filtrations. So it's some general result that central convolution exact object on affine flag perversions admit Akimoto filtrations. And now from this we get the monoidal functor from rep G check to T check to our category C. And just given by if V and lambda it goes to the central shift convolve with Akimoto. So and this is the input. So recall that in our previous discussion we need the input data is these monoidal functors. And now we are going to upgrade this functor to the equivalent direct category of a Springer. So there will be 4 steps. So first, the central functor has a tensor automorphism given by logarithm of monodromy because it's given by nearby cycles. So we have this tensor endomorphism of the central shift functors. And that's basically the step 1, the assumption in step 1. And then the second property is that for each lambda, there is an arrow from the central shift to J lambda, this Akimoto shift, satisfy the Plucker relations. Okay. And so this is also the basic follow from the restriction of Z lambda to the F L lambda, the corresponding orbit is 1-dimensional, basically. And this is basically the assumption in step 2. So, and now the property 6 says that there's a tensor endomorphism, and this arrow, they satisfy these equations. So M lambda tensor B lambda is actually 0. So it's made from Z lambda central shift to central shift and to Akimoto. This map is 0. This is basically follows from the tensor endomorphism is nilpotent. And the restriction of Z lambda to FL lambda, the orbit corresponds to lambda is 1-dimensional. And this is the assumption in step 3. And now finally, there's a Gurr functor, filtration functor on this category, which consists of object of Akimoto filtration. You take the filtration, you get a functor to representation of T check. And this functor satisfy the assumption in our previous step 4. So let me remind you that the last step we need. So we have these two properties that this functor is compatible with the functor we start with, and also satisfy this property. It's called conservativity property. Okay. And
can I ask? I just need a reminder how you show that the Akimoto filtration is functorial.
How to show? Well, it's functorial. It's unique.
It's the same reason that like a co-standard filtration is unique if it exists. It's just a simple Hom vanishing between
J lambda.
Akimoto shifts.
If lambda is
all right.
Yes. 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 So then we are good because now we construct our functor and we have all the assumption in step 1, step 2, step 3, and step 4. So construct all the require this assumption. Then so therefore, the property of central shift and Akimoto shift we obtain a functor from the equivalent direct category to this category DC, homotopy category of C, modulo cyclic complexes. So we just apply the previous general construction to our setting, and those property of central shift allow us to upgrade the functor to the equivalent direct category. And our desired functor, this phi diagonal, is given by, we have this, and we have a natural functor from DC to the bounded direct category of the perverse shifts. And later, and we have a natural functor from this direct category to the affine Haykett category. So it's realization functors. And so that's the construction of the functor, the phi diagonal. And so how many? There are some remarks about this functor, but maybe I don't have time to explain. So maybe just the part two, well, so first, the functor we construct is not T exact, but actually you can show that from this, you can show it's actually right T exact. And also this category C we introduce here also, or maybe it's this derived version. It's a geometric counterpart of the maxima obedient subalgebra of the affine Haykett algebra. And there are some comments about the last properties, this functor GERF. So probably have to skip this part. Okay, and so now we have this functor. And now our goal is to show that the composition of this functor with the Whittaker averaging functor to the Iwahori-Whittaker category, this composition is equivalence. And now let me just first recall some basic fact about Iwahori-Whittaker category. So we consider the opposite Borel here, and we can consider it's a preimage of the evaluation map, and this is a pro-unipotent radical. And we have this canonical map from the pro-unipotent radical of the opposite Iwahori to GA. And there we can introduce the Iwahori-Whittaker category on affine flag. So it's the equivalent direct category of IU minus this pullback. We have this Artin Schwarz on GA. You can pull back, you get the character shift on IU minus. And you can consider corresponding equivalent direct category. And this usually called the Iwahori-Whittaker category. And there are some nice property about this category. So first, you can consider the corresponding abelian category. And turns out we have this fact that the direct category is actually equivalent to the direct category of this abelian Haar. Some general fact about because basically IU is pro-unipotent. And also the IU orbits on this IU minus orbit on affine flag experiment affine extended affine Raoult. And for each W, you can consider corresponding standard, co-standard, and IC reduce IC shifts. And so we have the following fact that actually, so you can consider the minima length representative of the left coset, and we have a bijection between lambda and this minima length representative. And our Iwahori, this abelian Haar is actually a high weight category, and with a standard and co-standard object given by this. Okay, and finally, the most important thing is that we have this Whittaker averaging functor, I denote by AV per side, which is just given by convolution with this co-standard object. Okay. So convolution from the left, so give this Whittaker averaging. And this functor is T exact. And moreover, the induced functor on the abelian category is exact, and induce a full embedding of effectors through this quotient category. So the set of quotients. So here, the set quotient is this abelian category of perversion, equivalent perversion affine flag, modulo those set subcategory generated by LW, where W is not in the minima length represented. And this claims that this functor factors through this quotient, and the induced functor is a full embedding. Okay, so some fact about Whittaker, Iwahori-Whittaker category, and and the averaging functors. And so now the claim is that, so now we have this composition functors, we have this diagonal, p diagonal, and the Whittaker averaging. And the main result of the paper is that this composition is an equivalence. Okay, so and again, the main difficulty and interesting part is fully faithfulness of these functors. So it's kind of easy to see that this functor is essentially subjective, but to prove fully faithfulness, you need to prove some interesting result. You need to prove some other results. So therefore, let's focus on the fully faithfulness. So here's schedule proof. So basically, so this category admits some nice generator like the line bundle or this kind of free object. So therefore, to check fully faithfulness, turns out it suffices to check that the inducement on extension group is an isomorphism. You can check this on those generators. And now we have this fact that, so first, the extension group on the left actually is concentrating. If I is non-zero, then this is 0. If I is 0, then it's equal to the weight space, the dimension of the weight space, lambda in D. And so you reduce to check the case when I is 0, and then turns out the space on both sides have the same size. So basically, the right-hand side is also, the size is also, the dimension is also equal to this weight space, dimensional weight space. So therefore, to check that this is an isomorphism, it's enough to check that this map is injective for when I is 0. You check that this map is injective. And now for the reduction, you can replace, since any line bundles admit embedding to this free object for some W, representing G check some general fact about line bundle on Springer solutions. You can replace this line bundle here by just this free object. So therefore you reduce to check that this map is an injections. Okay, so here's some free object here, V. And now to prove this, we have to use the following result of Roman, previous result Roman, and also now there's a new proof. So by Roman, Simon Rich, and Laura Ryder. So basically, so we can introduce this quotient category of perversion of Van Vleck. So it's a module those objects who suppose has positive dimensions, and let N0 be a regular nilpotent or element in the dual Lie algebra. And then they prove the following interesting result, important result. So it turns out this category is equivalent, has a natural monoid structure, and it's equivalent to the representation of the centralizer of the regular nilpotent. And moreover, if you consider these compositions, you have central functors, and then your quotient, and you identify the quotient with the representation of the centralizers. These are just the restriction functors. So we have this result. And now from this, we are basically done, because so our functor, this functor here, where we want to prove that it's injections, it's given by this. So it's by definition. So your object here, you take the central functors, and then you take Whittaker averaging, but the Whittaker averaging factors through this quotient category, and the induced functor here is fully faithful embedding, so it's isomorphism. So this is a functor we want to prove. We want to show that it's injections. But now we are done, because because the last one, because of fully faithfulness, it suffices to prove that this composition here is injections. But by this theorem, these compositions, you consider this further composition. So from here, go to here, and then do the further quotients. Can be identified first. We have natural identification of this home with just the home between V and W, but you think of this as a representation of centralizers. And then the theorem here, the identification. So therefore, this diagram here, and together this theorem implies that actually this map is injective. So therefore, the composition is injective. And so we are done. So therefore, this is injective. The map here is injective, and the map, the functor is fully faithful. And now the last page. Well, some remarks. So Roman proved a generalization of this theorem to actually to any nilpotent element, not just the regular one. And then the proof use, for example, some heavy machinery like serial weight or with monodromic conjectures. But for regular nilpotent, they find a way to kind of something more elementary to avoid those heavy machinery. And now the essential surjectivity is easy. So basically, it follows from that the category is generated by these line bundles, and the image of those line bundles also generated this category. So this part is kind of easier than the previous one. So. And then we're done. So we prove the theorem, the equivalence. And so there are some main reference for this talk. So the original paper by Akimoto Shift, and also for Roman's paper, these are two realizations. And there are some other approaches of this equivalence. So let me mention two. So one is by Christophe. He gave another proof of Roman's Akimoto Roman's result using circle bimodule techniques. It's I think it's a PhD thesis. And there's another approach by Sam Reskin. I think it's also a PhD thesis. So I think it's called a chiral principal series category. And there he gave another approach, and I think he put more. He can. I think he worked with the true Whittaker category or semi-infinite flag, and he kind of upgrade this Bernoulli Akimoto Bernoulli equivalent to an equivalence of factorizable categories. Okay, so that's it. So I'll finish here.
Any questions for Tsao-Hsien?
Sorry, just
Well, a lot of.
Hi. Yeah, just a reference question on Chris Dodd's work. So he does something in that direction, but does he really derive this theorem in a different way?
I think he basically I think his approach is like this. So I think on both sides he considers some tilting generators, and he try to identify the endomorphism of the endomorphism algebra of tilting generator on both sides. And for this, he construct this kind of these kind of functors, constant Whittaker functors, to identify the endomorphism of the tilting.
So Zorger bimodule of the constructible side, Zorger bimodule description of the constructible side is, I guess, in this paper, my paper with Jouet.
Yes. Yeah. I think he do this for the main point is the coherent side. I think that's the main point for his paper.
Okay.
Yes.
I also had a question about the other reference. I mean, is he really giving a new proof of this statement, or is he just upgrading this one to a factorizable statement?
I'm pretty sure it's only for the anti-spherical.
Yeah, for the anti-spherical, not the.
Doesn't yes, he doesn't treat the full.
The Stamber.
But for anti-spherical, yes, maybe he does. But again, it's based on this paper with Jouet, which gives some sort of Zorger bimodules description of the.
Oh, I was asking about B, the Raskin one.
I know, yes, Raskin, I guess, is a different approach. So
To this
Yeah,
theorem?
different. Sorry.
Also, I think Raskin's thesis is also about the anti-spherical thing. But
Yeah. I'm asking, is he just upgrading this statement to like the factorizable statement, or is he actually giving a new proof of this statement?
I think he give a different, but first his object is different. He doesn't work with a affine flag. He works with a periodic. It's a semi-infinite flag. And
yeah, but that's what I'm saying. I think he's proving that one is equivalent to this one. He's not giving a new proof of this theorem.
yes.
I guess I can ask my question from before again now that context is there. So the fact that, I mean, the fact that gauge horizontal sheaves have filtrations by Akimoto were sort of built into how we were defining the category C in this functor F in the first place.
Yes.
But like, is there a general requirement that for a functor F to extend to a functor from G mod n, that F of V should have a filtration by F of lambdas, or is that just something that's used in this specific case?
Yes, you see, so somehow this part is kind of very specific to this situation. For example, I have these general discussions in the first part. Somehow the last step, I just make some artificial assumption. There's some Gurr functor satisfies some properties, but yeah, and this is the exact case for our situation is a affine flag, but I don't know in general.
Maybe it's worth mentioning, Ben, that there's a beautiful lemma which Tsao-Hsien mentioned, which is that anything central is automatically Akimoto filtered.
Oh yes, this is also some nice property on.
Kind of remarkable. So that's how Roman shows that, or that's how AB show that the central sheaves are Akimoto filtered.
Yes.
And I think they attribute that to Merkovich. Is that correct, Roman? That observation?
that the central sheaves are Akimoto filtered. I don't remember, maybe, but I want to make a comment about this. So just like so for tilting objects, well, there is a definition that these are sheaves which have standard and co-standard filtration, and an equivalent condition is that the star and Schlick restrictions to the strata are perverse. So some specific stalks and co-stalks are in homological, specific homological degree 0 if you normalize things properly. And so there is something similar here. So I think Akimoto filtration amounts to saying that some sort of well, if you restrict to the semi-infinite orbit and take complex particle homology, then you get a vector space in the homological degree 0, essentially. So one way to think about it is, if in terms of some basic p-adic groups representation stories, so then this so for Hecke algebra acts on sheaves on G mod U, and the central, so if you action of the central functor can be rewritten as sum of translations, and I think this Akimoto property is related to that.
So I remember, so Roman, you explained this to me long ago that this central functor is something that's very similar to this with this nearby cycles functor for Wimber degenerations from group to Gma U times Gma U brought over T. You
Yeah, that's like, yes. It's not
there's many similar properties, so it's kind of finite dimensional analog.
No, I think you can just, it's not like particular deep, but I think you can just embed this finite dimensional picture into this affine picture in the following silly way. So if you just take a regular weight, and then you take like a pre-image of GO4 orbit in the affine Grassmannian, and then if you caution by Iwahara, it's the same as to take just G mod B mod B. So you recover that situation.
I see.
Then it's so now if you take this stratum like Gur lambda generalizing to degenerating to the subset in the affine flag variety, and then if you kind of remove the closed pattern, so throw away most of the interesting information, then I think you're just left with this degeneration.
These members degenerations.
Right, this degeneration when. Maybe one way you can think about it is this, that you can, maybe there's a better way to say it, but I like thinking about it this way. So you take, imagine like you have constant family like G mod B with fiber G mod B squared.
Yes.
And then you consider for every element in the group, but can consider just the graph of this action of this element. So it's a sort of copy of G mod B, which varies inside G mod B square. And now you can compactify the group to the wonderful compactification, and then go to the deepest stratum in the wonderful compactification. So then you'll have, so geometrically G mod B will degenerate into this cycle with W components. So it's like Schubert cells times the opposite Schubert cell. And I think that's what you see here at the level of, so this nearby cycles shift, you can take nearby cycles for degeneration, it will be an interesting shift. So I think one buzzword is semi-regular bimodule. So I think if you take a corresponding bimodule with Lie algebra.
Yes, yes.
But so I think, yes, so I think that's what you see if you restrict to this open part.
Okay. But somehow for the finite dimensional group situation, the monodrome is not so interesting somehow compared to the central sheet. So
yeah, yeah, it's still there, but
not.
So
it's basically the kind of the central character for the corresponding Harshanga B modules.
No, I think it's still non-trivial, but yes, I don't know how to. So for SL2, I think you still see this Picard-Lefschetz situation.
Yes, yes, yes.
So it is, it is some non-trivial nilpotent endomorphism.
Oh, I remember. So I shared some personal story. So I told Jordi before. So my first meeting with Roman. So he gave me kind of 2 reading homework. So first is to read this book by Chris Ginsberg. It's a complex geometry and representation theory. And the second homework is to read this paper, Akipov Vazukanikov. And he even gave me the offspring. I don't know if you can see this. Maybe as a gift. So, but at some point I finished the first homework. But now, for some reason, for the second homework, I still don't have time to finish until now. So.
Okay, so I didn't know you still have the paper. That's really
yes, maybe to encourage me to
appreciate it. Yes.
So Anne asked, in the chat why are these called the Plücker relations?
Yes, actually, I think I replied in the chat. I thought you replied well to the question about why Plücker, because it's just for, you can give a similar. Okay, so to give a point in Gmod B, it's the same as to give a line, well, highest weight line in every reducible representation, but you can say it differently, saying that it's enough to give a line, so that in every representation, and then when you take tensor product, then basically the product of these lines. So you can, maybe I'm not saying it precisely correctly, but I think everyone can modify it to be a correct statement. But yes, and I think for you can also make a similar thing for Gmod P, and for Grossmanian, this will amount to Plücker relations. But the name Drinfeld, as I wrote in the chat, refers to this Drinfeld's generalized B structures, which, well, it's a technical tool for making sense of this shifts on semi-infinite flags. So that's where it's, so, there was a one Thingberg-Mirkovich, and then Gates-Carey, and so the Zastava spaces. But so there is a more like geometric way to think about it. You plug in a curve, and then you want to consider some compactification of the space of B bundles. And the point there is that you kind of allow, so again, you think about the B bundle in terms of G bundle plus this flag, but the flag now, well, it again amounts to giving highest weight sort of line in every representation, but instead of a line, we say invertible sub-sheaf, and the point is, if we said sub-bundle, then it would be a B structure, but we say sub-sheaf, and then it becomes this. It gives rise to this compactification. And I think it's, yeah, it uses similar ideas. So this idea to consider Gmod U bar and think of it in terms of this highest weight lines is borrowed from the methods.
And maybe just to be like extremely explicit. So the global sections on the Grassmannian are V of n times the ith fundamental weight, where I is determined by whichever Grassmannian you're considering. So we get a homogeneous ring with components in every positive degree. And this is generated in degree 1 by the Plücker coordinates. And the Plücker relations are exactly which products of these coordinates project to the same thing in the highest weight of the module of highest weight 2 times omega I, whatever. Like, if you take this right back down to Grassmannian, then you literally get the Plücker relations.
So there's a question from Ben. Right. No, I think so Ben is asking whether the object V lambda on Gmod N.
And with the appropriate number of tildes and hats and squiggles.
Sorry. N mod. So sorry. So N is what for you? What is N? Yes.
Just backward, or maybe
I see.
Springer resolution, yeah.
No, it does. So yeah, well, Springer resolution, yes, because whatever, if something maps to Gmod B, then yes. So the trivial bundle is pulled back from Gmod B, and if you have line bundles are pulled back from Gmod B. So the way kind of at least I'm thinking about it, is that, you know, so to constructive functions, we only build, we only use this highest weight arrows. So we don't use Akimoto filtration. We only use the fact, the first term on the Akimoto filtration. But then the fact that it extends to a filtration, it really implies this vanishing that somehow. The distance of an arrow allows you to relate things to G mod U bar, the affine closure of G mod U, but then this distance of the filtration really allows to prove this vanishing and get rid of the boundary. Yes.
Okay, any other items of discussion? If not, let's thank Tsao-Hsien again.
Thanks. And for keeping the paper that I gave you.
Yeah, I find this in my pusher.
I like that story. Thanks again for giving me the talk. And yeah, we'll continue with that full 2 realization starting next week.
Next week. Great.
See y'all.